Hello, friends. Welcome to Never Stop Learning platform. Myself, Anshu Srivastav, and I hope that you are all okay. Today, we are going to select one interesting topic, and that is communication engineering. So, let's start. What do you mean by communication engineering? The communication engineering concerned with sending and receiving the signals by the help of electronics systems from one location to another location. If you see the block diagram here, this is a communication systems and it has maybe single or multiple inputs, and in the same fashion it has single output or maybe multiple output. So whatever the signal we fed to the communication system, it may be amplify the signals, it may be do some process the signals, do some conversions the signals. So it depends upon the function of that communication systems. Okay, so let's start the types of communication signals. Number one is deterministic signal. Deterministic signals, it has two type. One is your energy signals, it may be also called pulse signals, and that is non periodic signals. The second one is your power signals, and that is a periodic signals. The second is random signals. It has also energy signals and power signals. So, on this session, we will discuss only deterministic signals, and random signals we will discuss in our next session. So, let's representations of energy signals. The first is your time domain signals. Just see the graph. The ft, your frequency ft is your time domain signal with respect to t. So ft is equals to a is your amplitude, or you can also call a magnitude. 0 is less than t1 and t1 is less than capital T, and ft is equals to 0 otherwise. Now let's come to the second point by using frequency domain signals. So your ft is your time domain signals and fw is your frequency domain signals. So this is the relations, and ft is your Fourier transform, how we can convert the time domain signals to the frequency domain signals by using Fourier transform. And Fourier and frequency domain signals is equals to the integral of negative infinity to infinity ft e to the power minus I omega t dt. So this is the relations. Now let's Fourier transform denotes by ft. If you see both the graphs, left hand side is your time domain signals and right hand side is your frequency domain signals. And please note that we are talking about the energy signals. Okay, so Fourier transforms gives representations of the signal from time domain to frequency domain. And one more thing, that why we are going to convert this time domain signal to frequency domain signal. Yes, we know that it is converted by Fourier transform, right? But why it is required? Now this is the question. So just learned that we can find the various frequency components contained in the given signals and the corresponding magnitude of each frequency components. By representing the signals in the frequency domain, we can find the total bandwidth required for the transmission of the given signals. So I hope it is clear to you that why it is required to find the total bandwidth required for the transmission of the given signal. Okay, and also we can get the magnitude of each frequency components, okay, in the frequency domain. I think you are aware of RF spectrum analyzer. This is also work as a frequency domain by which we can get the bandwidth of that signals and multiple things we can get from that spectrum analyzer. So now let's start by energy spectral density. This is the third uh, options by which we can represent the energy signals. So energy spectral density is a measure of how the signal energy is distributed over frequency. The energy contained in the given signals per unit bandwidth, that is joules upon hertz. So again, just see the relations here. So how we can represent the energy spectral density by these relations. Okay, and xf is the Fourier transform of the signals and f is the frequency. Now the fourth one is your ACF, that is called autocorrelation function. ACF here, R tau is equals to T2 minus T1, and this symbol is denoted by tau. So if the tau is equals to 0, that is equals to R tau is equal to 0, right? R0 is equal to R tau. So energy contained in the given signals. So this is the relations for the real energy signals. So the autocorrelation functions is a measure of regulating with which the given signal will exit. Okay, so higher is the regulating, more is the value of autocorrelation function or tau. Now let's we talk about the representations of power signals, that is called periodic signals. Now we come to periodic signal or power signals. We have already completed the energy signal. So again, we have to follow all that um, procedures. First, we will talk about the time domain signals. So harmonic frequency is equals to multiple of frequency components. Now see this graph. This is what? It's a periodic signals. Now second is your Fourier transform. Number one is your trigonometric Fourier series. Sorry, it's using Fourier series. So trigonometric Fourier series, this is the relations if you see. So a naught by 2 is your DC value, and sigma n equal to 1 to infinity range denotes large fundamental harmonics, and it is not used in communications field. A trigonometric functions series represents a periodic functions as an infinite sum of sine and cosine function. This is a mathematical techniques used to analyze periodic functions by breaking them down into simpler sinusoidal component with coefficient, and an and bn determining the contributions of each terms. Similarly, we will talk about the exponential Fourier series. It is used in communications field. This is the relations. The Fourier series gives the representations of non-sinusoidal periodic signals in terms of sinusoidal. Okay. We are approximating the given signals in terms of fundamental sine and cosines and their large numbers of harmonics. We can find various frequency contained in the given signal and the corresponding magnitude of each frequency harmonics. We can then find uniform analysis of any communication systems. Now the third point is that the frequency domain by Fourier transform. Now see the relation again. It's the same thing. The sigma, the sum of n terms from negative infinity to infinity, where Fn is the magnitude of impulse function, is controlled by Fn. Sum of n terms is from negative infinity to infinity. The Fourier transform of or a Fourier spectrum of any periodic signal is a series of impulse function whose magnitude is controlled by exponential Fourier components. Now the fourth one is that power spectral density GPW. So the power contained in the signals per unit bandwidth is watt per hertz. See the relations here. The P is equals to 1 upon 2 pi integral infinity to infinity G P W dW. The power spectral density PSD of any periodic signal is a series of impulse function whose magnitude is controlled by exponential Fourier coefficient denoted by Fn. Using the PSD, we can find the total power contained in the given signal. Using autocorrelation function ACF, this is the same terminology. Okay, see the relations here. Now, let me zoom out. Now, if you see the relations here, R tau is the autocorrelation functions for the time lag tau, xt is the periodic signals, t is the time lag, and capital T is the fundamental time period of the signal. Now these are the graphs, periodic signals, sine wave, triangle wave, and square waves. And if you see, these are the graphs here. Even frequencies are there, odd frequencies are there. So we talk about the periodic signals again and see the graphs here on the below. A periodic signal is a signal that repeats itself a regular interval of time. A periodic signals can be represented as the sum of sinusoidal function with frequency that are integral multiple of fundamental frequencies of the signals. The fundamental frequencies of a periodic signal is the lowest frequency present in the signals. The periodic signals are important in many applications because they have a well defined frequency spectrum and that can be easily analyzed using tools from Fourier analysis. The period and the frequency of the periodic signals are inversely related. A signal with the short period has a high frequency, and a signal with a long period has a low frequency. The non-periodic signals, a non-periodic signal, just see the graphs here, it is not in a uh, proper time interval. So a non-periodic signals that does not repeat itself at a regular intervals. This means that it does not have a fundamental frequency, and its frequency spectrum is generally not composed of discrete frequency. Non-periodic signals can be continuous or discrete, and they can be either deterministic or random. Examples of non-periodic signals includes white noise, impulse, and arbitrary waveform. Non-periodic signals are often encountered in real-world applications such as speech, music, and environmental noise. Now, the summary what we covered during this session, we talk about communication engineering. Then types of communication signals we completed, deterministic signals, random signals discussed in next session. Deterministic signals, it has energy signals and it is pulse signals we called. Again, power signals, it is called periodic signals. And the time domain signals versus frequency domain signals by using the Fourier transforms we covered this time. The Fourier series means we have trigonometric Fourier series as well as exponential Fourier series. The power spectral density, which is covered for both deterministic and random also. And the last one is your autocorrelation function. I hope this session is important for you guys, and we will get more content on this communication engineering. Thank you very much guys for your time. Thank you watching my never stop learning platform. Viewers, please like and put your comments to upload more useful contents. Thank you. Have a nice day. Bye.